Cool. So, hi, my name's Andrew. I'm here to talk about my work on parallel sequences in Multicore OCaml. So the parallel sequences abstraction is a abstraction that's inspired by parallel collection abstractions that are found in many other languages, like Nestle or Data Parallel Haskell or Scala. So this is a pretty common abstraction. And what this is it's an abstraction that lets you leverage parallelism using very simple operations that are actually very similar to the ones that you might find in like a list or an array module. So for example, the tabulate operation, it's the first one on the slide here. It's an operation which just takes a function and an integer n, and it creates a new sequence by applying the function to every single integer between 0 and n-1. And so this is very analogous to like a list.init, with of course the exception that all of our initialization functions are actually being applied in parallel. So this is a very familiar operation that's parallelized. Next we have a map, which of course is just like a list.map. It applies the function to every element of the sequence. But of course, again, all of our mappings are actually done in parallel. And then finally, we have a reduce. So the reduce is more or less analogous to a list.fold_left or list.fold_right. But the difference is that the function provided has to be associative. So when we apply it in parallel, we can actually apply it in parallel instead of sequentially. Right? So now let's look at an example program that uses some of our functions. So we have this somewhat contrived example program, harmonic sum, which is just going to take the first n terms of the harmonic series and then sum them together. So we might start first by creating a sequence in parallel for all of the denominators that we're interested in. So we have just 1 through 5, right? And then what we might do is we might map all of our denominators to their reciprocals in order to get the terms that we're interested in. And then finally, after we've done this, we can just reduce them all together. So we can see here, as a client of the library, we're not really doing anything different than how we would have done this using a list module. We're just calling the library functions and letting the library take care of the parallelism. So we're allowed to basically leverage this parallelism with essentially no additional implementation effort. So so now we've seen an example. Let's talk more about the actual shared memory parallelism in OCaml. So for the unaware, in OCaml 5, there's this new primitive called domains, which were introduced and they can be worked with using the standard library module domain. And really all a domain is just it's a one-to-one map to a OS thread. So it's a heavyweight entity, and it's expensive to create and tear down because every domain keeps their own internal state for things like memory allocation. And so since it's a little heavyweight and sometimes a little awkward to work with, there is a higher level programming library that's recommended in the manual, which is domains_lib. So domains_lib is just a work stealing queue, and it has some domain pooling. And what it does is it just offers some pretty basic parallelism primitives, like an async await, and also some pretty useful parallel iteration constructs. And this is actually the library that parallel sequences is built on. So parallel sequences is built using some of the parallel primitives from domains_lib. So let's talk a little bit about the implementation. So first, I'll talk about tabulate, which is arguably one of the most important ones, which creates a sequence, right? And so first, it's good to know that the underlying type for a sequence is an array. We're going to put all of our computations to the array, and that gives us constant time indexing. But of course, the type is opaque, so it's abstracted away for the users. But the domains_lib parallel_for is very useful here, right? We can use this parallel_for to just call our initialization function in parallel. And then, of course, when we're actually getting the result, we can just put it into the array at the appropriate index. And so you might notice that we actually need to have an array to put our function into. And so this getInitializeArray function needs to be able to return an empty array. And notice the tabulate function doesn't take in a default value. So we need to be able to create an uninitialized array without a default value. So the array.make here doesn't work. And so what we can do is just do an array.make for an integer 0, and then call obs.magic on it to make it an array of any type. And so this is a very simple way to do this. There are certainly more efficient things, and of course this is not the best, but just to get an understanding of why we might be able to do this, it's good to know that in OCaml, the last bit of every word is what the garbage collector uses to tell apart integers from pointers. And so this is a perfectly safe operation to do because the garbage collector won't treat the 0 as a pointer. And we don't actually really need to do an array.make here. We can actually use a cstub. So the array.make, of course, it has to actually do a couple of extra checks. So whenever we want to put a pointer into our array, it has to do a few checks to see if it's a pointer, to make sure that we're maintaining things for the memory garbage collection later on, just to have pointers from the major heap to the minor heap. There's some extra checks, and our C stub can save time by just skipping these checks. So we have a slight optimization over array.make. But even though we have this optimization, we still do need to set every single field of our block before we return. The reason why is in our C stub, any uninitialized block that we allocate has to immediately be filled with well-formed values before we return. All the fields must be set to either some kind of safe pointer or to a integer value. So it has to end with a 1 in its least significant digit. This is because if we returned it with just uninitialized data, the garbage collector could see our pointers, our garbage as pointers, and then try to dereference something and then segfault. But unfortunately, there's not really a very good way to actually initialize every single field in parallel. We need to set it to some safe value like unit, but there's not a good way for us to parallelize this. And so we actually do take our sequential hit here. We have to go through and set every value to some safe unit. But this is a very optimizable operation. It is really just going through and setting every value to unit to 0, 0, 0, followed by a single 1. So this is pretty efficient. And although it's unfortunate, it's extremely negligible for most reasonable applications. And I'll talk about this a little more in the limitations section. All right, so now that we have tabulate implemented, we can implement a few very useful functions very directly from tabulate. So for example, there's an append function, which just takes two sequences and then appends them into a new sequence. And it's very easy to use just a clever body function in order to use tabulate to do this in parallel. So if we just check the index before we figure out which sequence to take it from, we can just get it from one of the sequences, the correct sequence, and then tabulate a new sequence. So this is very efficient. And we can see that since tabulate is done in parallel, append is also very trivially done in parallel. And map is similar, and there's a couple other operations that are very similar. So now let's talk about reduce and scan. So reduce is just like a list.fold, like we said earlier, but then a scan is just, it's a prefix sum operation where every single index I in the new sequence will contain the prefix sum all the way from 0 to I of our input sequence. And these are both implemented using the classic Ladner and Fisher parallel scan algorithm. And reduce can be done by stopping halfway through the algorithm and combining together the necessary partial sums. And so the diagram below is not the implementation, of course, but it's just like a diagram that kind of shows you what the actual functions are intended to do. Right. So for the reduce implementation, what we can do is essentially reduce things together in layers. As we see here, none of our arrows will overlap from layer to layer, and so we can actually do all of our layers in parallel. And then, of course, since we're dividing by 2 each time, this is a logarithmic depth. And at the very end, we can combine together our partial sums that are necessary. And the number of partial sums we combine together sequentially is always logarithmic. So this has a logarithmic depth here. And then we get our combined together values at the end. That's our reduce implementation. So then finally, if we see this bottom layer of the reduce, what we can do is continue the Ladner and Fisher algorithm to this scan. So the scan starts with the same half, and then it just continues until we are basically collapsing this back down into a prefix sum at every index. And so as before, we can see every layer has non-overlapping arrows. We can do all of this in parallel very efficiently. Right. So both reduce and scan can have this logarithmic depth. So next, let's talk about flatten. So flatten is just like a list.concat. It just takes a nested sequence of sequences and flattens it out into one single sequence. And the way you can do this is pretty simple. We can first map all of our sequences to their lengths. And then once we have all of their lengths, we can do a scan over it to get our cumulative lengths. So now we have the cumulative lengths up to every index. And note that our scan is actually an inclusive scan. And so we want to shift it to the right one just to get to the final offsets into our final array that we're going to copy it into. And now that we have the size, which was the last index of the inclusive scan, as well as all of the offsets, we can just copy it into our final array in parallel. So this is relatively straightforward. Finally, let's talk about filter. So filter, we want to take a predicate and a sequence and essentially create a new sequence where only the elements that pass the predicate are kept. So this is just like a list.filter. And finding out which elements to keep is relatively simple. You can very easily see doing that in parallel, but keeping them is a little less straightforward. So what we end up doing is first we map to a 1 for true or 0 for false. So this is like a bit vector. And then once we've done this, we can do an inclusive scan across our entire bit vector. And now that we've done this, we can see that at every index, what we've essentially said is we have how many elements we want to keep that are to the left of that, of offset by 1 for the ones that are included. And so what that means is we can go through and we can see which elements we want to keep using the bit vector as a metric for which one we want to keep. And then the index we can find by subtracting 1 from the values from our scan. And so then we can copy it into our array in parallel again. Right. So now that we've talked about the implementation, let's talk about, of course, performance. So a couple of metrics. First, the metrics we have. The first metric we have is this block matrix multiplication. So what we're doing is just multiplying two float matrices, each of size 2000 by 2000, using blocks of size 100 by 100. And they're both float matrices. And this is a classic parallel benchmark, and it parallelizes very well, and it has very good locality, right? And so as we see here, even though we haven't really had to think too much about parallelism, we can still get pretty good performance speed up. And note that in this metric, the only source of parallelism being leveraged is the parallel sequences interface. So there's no actual thought about how to actually parallelize things or schedule things. We're just calling those basic functions. And just a quick note, the comparison here, the speedup is being measured to a purely sequential implementation. So this is the speedup that we get over what would be a completely sequential implementation of the of our basic operations. Right. So now for a completely different kind of application, web indexing. So web indexing, what we're going to do is create an inverted index using from a file of pages. And what it'll do is it'll map words to their locations in all of our pages. So the steps are pretty simple. First, we just parse all of our pages into maps, binary search trees, which just maps every single word to a set of locations in the documents. And then we can actually just reduce all of our binary search trees together. And so it's worth noting that there are certainly much more optimal ways to do this, particularly some of the binary search tree reducing, as well as the sets being combined together. But to show the simplicity, I've literally just been calling map.union and set.union. So we have very simple implementation. And even though that's the case, we still get pretty respectable speed up, even with such a complicated reduce. So this was performed on a file of about, that was about 800 megabytes. It was 1 million pages. And we see that we get very respectable speed up, even though it was a much more complicated type of application, a less idealized application. So finally, let's talk about a couple limitations. So one of the first limitations is a dependence on domains_lib. So domains_lib is a great library, and it does very useful things for the parallelism primitives. But unfortunately, there's not a way for us to influence how tasks are actually scheduled onto the domains. So what that means is we can't actually tell domains_lib to schedule a task for a certain domain. And what this means is sometimes we lose a little bit of time in memory locality missing. For example, let's say in our harmonic sum operation from before, we would want to do a tabulate and then followed by a map and then followed by a reduce. Well, ideally, we would have that the domains doing the domain responsible for a certain chunk of the sequence doing a tabulate would eventually also do that same chunk using the map for memory locality. But unfortunately, we aren't able to actually influence this with domains_lib. So it's certainly possible that future work could abandon dependence on domains_lib entirely and actually maybe have a more custom scheduler that is a little bit more smart with these kinds of decisions. And then next, as I alluded to before, I want to talk about array initialization. So for many reasons, with how the memory model, as well as the way that the garbage collector threads atomically mark our objects during garbage collection, and a few other things, unfortunately, it's simply not possible to create array in parallel in the current OCaMl runtime. It's not supported. And in fact, even the recommended higher level programming library, a parallelism library, domains_lib, it has a call to array.copy, so a sequential copy, in its function task.parallel_scan. So we're trying to do a scan in parallel, and we still have to wait on a sequential array.copy. This certainly is extremely unideal, and the rest of the time I'm going to spend is going to be talking about ways that we can get around this, because this really is something that's an unfortunate aspect of working with parallelism in the new Multicore OCaMl. So first, somewhat of a trivial approach to saving time on array creation is to create less arrays. So sometimes creating a new array for every intermediate operation is unnecessarily expensive. In our harmonic sum example from earlier, the only thing that we cared about was the actual sum, but we were still having to create our arrays for every step. and we have to create a new one to keep things functional. My interface is purposefully functional, but that sometimes is a little bit expensive unnecessarily. And so it could be nice to have some in-place operations which just will do these things in place rather than having to wait on creating another place to put all of our work. To illustrate this point, I've gone ahead and I've made a new function called in-place_scan that is there to kind of replace domains_lib task.parallel_scan. And what it is it just takes the array.copy, which was actually only there to keep things functional, and it just removes it entirely and then modifies a couple things to make it work. And well, now we have an in-place scan. This is the blue line here, and we can see that we're actually saving a significant amount of time when we have a large number of domains. So this is calling task.parallel_scan from domains_lib on a array of 1 billion integers, and we're just doing integer addition. And we can see by just taking out the array.copy, we have a very noticeable performance increase in terms of scalability for number of domains. And so we can see that there definitely is some kind of promise to removing some of the sequential stuff for very trivial, fast, like very trivial operations like just integer addition. And then finally, some more permanent solutions that are still functional. So one potential array creation solution is after we create an empty block, we could use an anonymous mapping to set all the values of the block in 0, but not actually go through and do this at the time of the creation. In theory, the page faults should be distributed across the domains, but this is not exactly cheap either, and it's actually unclear whether or not this would actually make this much faster. And it's also worth noting that this would actually require modifying the garbage collector in several places just to tell it to ignore null pointers. So as I mentioned before, every time the garbage collector sees a word that is least significant bit 0, it's going to assume that it's a pointer. And then if we just did the memmap now, we would unfortunately have a bunch of null pointers and the garbage collector would immediately segfault. So we'd have to modify that in a few places. And then a little bit more of a straightforward solution is to use an array of arrays. So the added cost is 1 extra indirection per access. So unfortunately, that does bring on a cost on that scale for the accesses, but it does make the distribution of initialization work much easier, right? Because we can just have our chunks done sequentially by each domain, but not having to worry about actually creating the array in parallel. And this also makes the marking workload a little bit more balanced. I kind of skipped over this, but even if we have an array initialization done in parallel, eventually we're going to have to garbage collect this array. And currently marking in the parallel garbage collector does not actually do marking incrementally. It does marking one block at a time. And so if you have some gigantic sequence, even if we manage to initialize that in parallel, if we just have some gigantic array, eventually one domain is just going to get unlucky, and we're going to wait for that during garbage collection, stop the world. So that certainly will make the marking workload a bit more balanced. This is, yeah. But to conclude, this parallel sequences abstraction is still a very simple abstraction for using the shared memory parallelism in the new Multicore OCaMl, and we get very respectable speed up for basically no additional implementation complexity. We get to use very familiar paradigms from functional programming to leverage parallelism without really having to think about it. And even though the limitations are unfortunate, most of these are very small and pretty negligible in most reasonable applications. And yeah, while there is not currently an OPAM release, there will be in the near future, and for now, all of the code is in a public GitHub repository. So yeah, with that being said, I'll now take any questions.
Drew? Question?
So I'm not going to speak about magic because problems there, but thanks for the talk anyway. But I was rather, I have a question why you want to create arrays at every map rather than delaying the creation of that at to the reduce or something like that, and compose the function in your type and just apply the map during the reduce.
I see what you mean. Are you asking like about a map reduce function, or are you asking about? Sorry, could you explain a little more? I'm sorry, maybe I didn't catch that.
So your type sec doesn't have to be an array. It could be an array, a pair of a function and the last data structure that you did actually construct, and just actually compute the value of that type when you need to actually read it.
Right. So what you're proposing is that rather than having the computation done as soon as it's applied, we just kind of like add this to a queue of functions and then we apply it as soon as we need it. Did I understand that correctly?
Yes.
Okay, so yeah, that's a very reasonable approach, and this certainly would make this a little bit less expensive. But something that is worth saying is that this is not exactly how you would be working with a normal with a normal module like list. This is kind of more analogous to doing things lazily, right? We're just trying to force it as soon as we actually want the value. And I think the approach that I was going for here was a little bit more that we wanted to actually have the function being called as soon as we called it. This is definitely a very reasonable approach, but it wasn't really the intent of the interface.
I have a sorry. This is Richard Eisenberg from James Street. When you do array initialization, isn't there a problem maybe with floats and flat float arrays? Okay, so others are nodding. Have you tried this with floats? I think you might run into trouble.
This does work with floats. I'm sorry, what was the issue? What is the issue that you're concerned about?
So if you put a float into an array, if you make an array of floats, it the garbage collector doesn't normally scan it. But if you in your case, if you fill it all with zeros, it will mark it as a scannable array, and that if later you put in a float, you might have a float whose bottom bit is zero, and then the garbage collector will try to traverse it and hit a brick wall.
I absolutely see what you mean. Right. So this isn't exactly what's going to happen. So what you're talking about, you're talking about the non-scanned flat float array that's offered by the array module. So under the hood, the way that that works is the tag bit. So the tag byte in the word preceding all of the blocks. There is actually a specific float array tag. So what I'm actually using is the array tag. It's always just the zeros tag. The float array tag is actually a specific tag that tells the garbage collector not to scan that specific array. And I agree that that would be a problem. Unfortunately, the way that things are working with right now is we just don't have the flat arrays. I see that is absolutely not ideal, but it won't cause any problems because essentially what we have here is instead of a flat float array, we now have an array of boxed floats. Under the hood, when the actual runtime for the array checks the tag of the array to see whether or not it's one of the flat float arrays or the actual normal array. And if it is the flat float array, it does that optimization to put the float in. But we won't actually have the direct float values into one of the created arrays because we'll just have a boxed float. It's not ideal, but it still is correct. Like it won't crash because of that.
Okay, thank you.
Yeah.
So thank you, Andrew.
Yep. All right. Thank you.